Hi, welcome to Expertise Academy. This is Giri, lecturer in physics. In this video, we discuss about the force on a current carrying conductor, which is a magnetic field, and also Fleming's left-hand rule. See the first topic in this video: force on a current carrying conductor placed in a magnetic field. See this picture. These lines indicating the magnetic field lines. Magnetic field lines. And consider a current carrying conductor. This is the direction of the current. Capital A is the area of the conductor. Small d is the diameter of the conductor. And v is the speed of the charged particle here. At the same time, we consider small length, that is dl, out of the total length, that is l. Consider small length dl out of total length l. We have to observe the force at this dl point. Force at this dl point. Okay, and also the angle between the face or surface of the conductor with magnetic field lines, that is theta. Okay, look at here. Force on a current carrying conductor. Force on a current carrying conductor in a uniform magnetic field. Force on a current carrying conductor in a uniform magnetic field. See here. Force experienced by each electron in the conductor. Force experienced by each electron in the conductor is F is equal to minus E, that is charge of the electron, into drift velocity into magnetic field. This is equal to force experienced by the charged particle in magnetic field. Okay, so F is equal to minus E into Vd cross into B. Vd is the drift velocity. This is the vector form of the magnetic force which is experienced by the each electron in the conductor at magnetic field. If n be the number of density of electrons, n be the number of density of electrons. So here small n is there, that is density of electrons. I mean number of electrons is small n. Okay. Here number of electrons is only one. Capital A be the area of cross section of the conductor. Then number of electrons in the element at dl, that is n a dl. This is the small n is the number of density of electrons or number of electrons, area of the conductor, small length of the conductor. Force experienced by the electrons in dl. Force experienced by the electrons at the place of dl. At this place, we have to find the small amount of force. Why here representing small amount of force? This is the small amount of length. This is the small amount of length. So df bar, that is equal to n a dl into minus v into vd cross b bar. There is a magnetic force for small n density of electrons at capital A area of conductor, dl length of conductor. So finally, df bar, that is equal to minus n e a vd into dl bar cross b bar. So finally, we get the relation df is equal to I into dl bar into b bar, where I is equal to ne capital A vd, and negative sign represents the direction of dl is opposite to that of drift speed or drift velocity. So here current passing through the conductor, that is equal to product of drift velocity and NEA. N is the density of electrons, that means number of electrons, charge of the electron, area of the conductor. Okay. So finally we have the relation of the integration process. Capital F bar, that is equal to integral df bar, that is equal to integral I into dl bar into b bar. So finally we get the vector form of the magnetic force of the charge in conductor. F bar is equal to I into L cross B. Or finally, F is equal to ILB sin theta. ILB sin theta. If theta is equal to 90, magnetic force that is equal to ILB. If theta is equal to 0, magnetic force is minimum. Theta is equal to 90, magnetic force is maximum. Theta is equal to 0, magnetic force is minimum. So this is the force on a current carrying conductor placed in a magnetic field. See this, if the conductor placed along the direction of the magnetic field, angle, then that is equal to theta is equal to 0. Hence the force experienced by the conductor is 0. Before that I said if theta is equal to 0, magnetic force is 0, that is minimum. So when it is happened, if the conductor is placed along the direction of the magnetic field, conductor is direction of magnetic field, angle is equal to 0 degrees. Hence force experienced by the conductor is 0. If the conductor is placed perpendicular to the magnetic field, conductor direction is perpendicular to the magnetic field, then the angle theta is equal to 90 degrees. Hence the force experienced by the conductor is maximum. Here F total, that means total maximum force or total magnetic force, that is equal to BIL, that is Bill. Okay. So this is the information about the force and a current carrying conductor placed in a magnetic field. Coming to the Fleming's left hand rule. Fleming's left hand rule. See this picture. This is the left hand, thumb, forefinger, middle finger. Fleming's left hand rule. See here. It is possible to predict the direction of force acting on a wire with motion if the direction of the current or the magnetic field are known. Fleming's left-hand rule is used to this. See here. Thumb represents the motion of the particle or direction of the force applied on the particle. Next, forefinger represents the first finger represents the magnetic field. Here, middle finger represents the current carrying by the conductor. See once again, this is the left hand. You have to keep your left hand fingers, particularly thumb, first or second fingers. First finger or fourth finger, second finger or middle finger. Any two fingers in perpendicular. Okay, any two fingers in perpendicular. At that moment, thumb of the left hand represents force applied on the conductor or motion of the particles. Next to forefinger or first finger represents the direction of the magnetic field. Forefinger or middle finger or second finger represents the direction of the current. Direction or speed of the current also. Direction of the current or speed of the current or charge particles also. Okay. So this is the Fleming's left hand rule. So in this video we will discuss the two topics. So what are the force on a current carrying conductor placed in a magnetic field. When the conductor is placed in a magnetic field, at that moment the magnetic force applied on the charge inside the conductor, that is equal to F is equal to ILB sin theta. F is equal to ILB sin theta. At this particular moment, when direction of the magnetic field and the conductor both are parallel, theta is equal to 0. At that moment, magnetic force applied on the charge inside the conductor at magnetic field, that is equal to 0. Simply F is equal to 0 when theta is equal to 0. When theta is equal to 0, magnetic field direction, conductor direction both are parallel. If conductor is placed perpendicular to the magnetic field, theta is equal to 90, then sin theta is equal to 1. Magnetic force applied on the charged particle is maximum. So F is equal to 0. Next, Fleming's left hand rule. Give your left hand three fingers, thumb, first and second fingers. Thumb, first and second fingers like a perpendicular manner. So here, thumb represents motion of the motion of the particles or force applied on the particle. First finger represents field, magnetic field direction. Middle finger represents speed of the charged particle or current, direction of the current. So this is the information about force applied on the charged particle inside the current and also Fleming's left hand rule. Thanks for watching this video. For more videos, visit www.expertiseracademy.com.